So, in this lecture we will deal with one of the most important random variable that you will ever encounter, and that is called as the Gaussian random variable. Also it is called as the normal random variable. The distribution is called as the Gaussian distribution or the normal distribution. The reason, as you will see later, why this random variable is so important is because of a theorem called as the central limit theorem, which tells that if a number of identical independently distributed random variables, if you take and then sum it over, and then there in asymptotic limits, they will converge, their sum will converge to Gaussian distribution. We will take up that central limit theorem and theorems which talk about it, called as the law of large numbers and so on, little later. But right now we will treat it as a continuous random variable and then look at its properties and so on, and to that extent we will do it now. Later we will again and again encounter it, this Gaussian random variable. One more important thing is that when we looked at the binomial random variable, then we saw that under certain conditions the binomial distribution can be approximated as a Poisson distribution. It can give a Poisson distribution to be a limiting case of the binomial distribution. Okay, when n tends to infinity, p tends to 0, but np is a constant and so on. We will see that in another limiting case, the binomial distribution can be approximated as a Gaussian distribution. So in that case, in that sense also, Gaussian distribution plays a very important role. So first, we will, x is a random variable and it is normally or Gaussian distributed. Okay. So usually we have a notation for it. Bernoulli, geometric, Poisson and so on, exponential and so on. In this case, the notation that we will use is n, capital F, to stand that it is a normal distribution. It has two parameters, which we will put it within bracket of this normal distribution. One parameter is called as mu and another parameter is called as sigma square. So there are only two parameters that completely define this Gaussian distribution or the normal distribution. And to indicate that there is a random variable that has Gaussian distribution, we will use this notation. Okay? So, when do you say, first of all, every random variable has got a support. This is also something that you should, it will be mentioned in many literature, you should understand. What it means is that the values that it can take, that this random variable can take, which has got non-zero probability. For example, if you talk about the exponential distribution, random variable x exponential with the parameter lambda, the support is 0 to infinity. It can only take non-negative values. Whereas for a Gaussian random variable, it can take the whole range of the real axis. Any value is a valid one. That is one. Then, how do we define it? We give a prescription for the probability density function of the Gaussian random variable and then tell that any random variable that has this form of probability density function qualifies for to be called as the Gaussian random variable. That is how we will start up with. And then we will look at what properties it has got and so on. So the probability density function of x, how do we write it? F small capital X subscript of x is given by, because it has the whole real line as its support, there is only a single formula which is valid for all x. Okay. So that is given by the following formula: 1 over root of 2 pi sigma square into e power of. So just you can put e Okay, if it is an e power of minus y by 2 or something, we can use this notation. If it is a little larger expression, you can use this one within bracket. It's all one and the same. E power of, so this is the exponent, minus 1 by 2 into x minus mu the whole square by sigma square. So this is, if you want, I can put it here to clearly indicate that there is a negative sign. Or if you want, if you are able to comfortably write it, you can write it like this also. One more thing is, this sigma squared is within the square root. So another way in which you can write it is, you can take it out of the square root and put it like this. That is also valid. But you have to be very careful whether that either sigma squared has to be within square root, or if you take it out, you should not extend this line. And e power of minus so this way also you can, same thing. So if this is the form of the probability density function of the normal distribution. Now let's try to understand how this function will look like. Ankit, is this so? Huh? You call him, you have to read here. Or you call Rohan or someone. So how does it look like? First of all, this function. So if you look at this function, first thing is that is does it have a symmetry? Okay. If you plot it, does it have any symmetry that you can look for? Yes, it is symmetrical above x equal to mu. Why? X minus mu, see, all these are constants. Sigma squared, this sigma squared, of course mu is also a constant, everything is a constant. A variable occurs here only, in this form, and that is the one which is going to dictate the form. So it is x minus mu, but there is a whole square. So what matters is how much x differs from mu. And you are going to take a square of it. Once you know that value, everything is known. Okay. So whether x is less than mu or whether x is more than mu, as long as the difference between x and mu is a given quantity, the value of this function is the same. Okay. So it is symmetrical about mu. Number one. And when will it achieve the maximum value? So if you look at it as a peak, it has to be a normalizing function. The function has to be normalized because it's a probability density. So it cannot be monotonically increasing or decreasing and things like that. Okay, if it is monotonically decreasing, then it has to be normalized. That is very important. So it can go, it may not drop to zero. Even at infinity, it asymptotically go to zero. That is also allowed. It has to be convergent. That is very important. So assuming there is a peak, where is the peak? The peak again is at mu. Because when is this function maximized? This function is maximized when this is minimized, because there is a negative one, and this is minimum. Okay. Then so when will it happen? So the value that it can take is, it's always a negative one. Okay. So the maximum value it can take is 0, and that will occur when x equal to mu. Okay. When x equal to mu, this is 0 and the whole thing is 0. But x, if it deviates from mu, then this is positive, everything else is positive, there is a negative, it is always a negative, then it will be less than. So it is max equal to mu is where you get look for the peak. And as x deviates away from mu on either side, this quantity as x increases, deviates, goes away from mu on either side, this quantity increases and e power of minus that quantity decreasing, so it has to drop down as you move away from mu. So with all these in mind, we can draw the Gaussian distribution. So this is where x equal to mu is, and at mu what will happen? This will be, the whole thing is 0. So it is 1. So the only factor is 1 over root of 2 pi sigma square. Whatever that value it is, and that will be the peak value. So what is the actual numerical value of it? 1 over. And then it has to symmetrically drop down asymptotically to infinity, to 0 at infinity on both sides. So this is how it looks. So this looks like a bell. So more often we, in a common sense, we will say it is a bell-shaped curve. So this is one thing that we need to understand. Next, what will happen for different values of mu1, mu2 and mu2, where all having the same sigma square. So the sigma squared is going to decide the shape of this bell-shaped curve. The role of mu is only to fix the point at which peak is, as long as the sigma squared is same. So if we have mu1, mu2, mu3, say let us say this is 0. Mu can also be negative, it can be any positive values also. So if you, for the same sigma square, so here the curve will be something like this. Here for this it will be like this. And here it will be like this. So mu fixes the peak. As you change mu, the curve shape remains the same, it just shifts. Yeah. And what will be the effect of sigma? Well, two values of sigma. One we will call it a sigma 1 square. Another we will call it a sigma 2 square. Sigma 1 square being larger than sigma 2 square. Same mean mu. Okay. So the peak occurs at what? 1 over root of 2 pi sigma square. So for this one it occurs at a higher place. Okay. Sorry. Peak occurs at when sigma is larger, the peak is smaller. Look, 1 over root of 2 pi sigma square. When sigma is larger, peak is smaller. So for sigma 1, it should occur somewhere here. For sigma 2, it should occur somewhere here. That is one thing. Then what happens? So that is one thing. So the peak should appear and then it should drop down here also. Shall we draw like this? Is a question. Why? Area. There are two arguments. One, decays is something that we have to worry about. Another is the area. We know it has to be, it represents a PDF, it has to be normalizable. Area should be the same. So if you look at this, any region like this one, for this region this is a smaller area, this is a larger area. To compensate for that, Okay, this has to drop down, cross over, and then go below this cut after some time. Then only both will can have the same area. Okay, so that is one. Another thing is the so we will retain that this is the curve for the sigma 1, sigma 2 correspondingly of the curve. Another thing is that look at this e power minus half x minus mu the whole square by this. It reaches maximum at x equal to mu, and see when it is very small, okay, then it will have here when x is quite distinct from mu, okay, then this quantity is larger and we are taking a square of it, and that goes as e power of minus, a large quantity divided by it. So what is the role of the sigma squared here? Okay, it decides, and comparing the magnitude of x minus mu the whole square and sigma square, okay, when it will tell how much this has to be larger for it to reach a given value. For example, if you are looking for e power of minus half, so both are one and the same. Okay, this quantity should be equal to this quantity, then only that will be achieved. Larger the sigma square, then more has to be the deviation in order for that to be reached. See, if you look at what values they will have the same magnitude, you can say that there will be one thing e power of minus half, and both of them are going in the same. For that to happen, look at when sigma is larger, this deviation should also be larger for that to take place. Okay, so that is one thing. So this one again, because of that, what will happen is this one should be dropping when sigma, what are we taking? Sigma 2 is smaller, sigma 1 is this one. So it has to be like this. So the larger the variance, then flatter the curve is. Sigma 1 is larger, flatter the curve. Smaller the variance, it is peaked. In the limit sigma tends to 0, then what will happen is it should be something like this. It will be what is called as the direct delta function. Which is again a one which has value non-zero only at x equal to 0. Now it's mu. And the area under this curve is 1. Okay. So in that case, it will only take a value mu with sufficient probability, non-zero probability, which means that it becomes a deterministic quantity, taking a value mu with some probability, and any other value is not probable. So sigma tending to 0, a normal distribution becomes more and more like deterministic. You can predict what values, range of values it is likely to take. But when the sigma is very large, then it becomes more flat. In the limit of very large sigma, that it can equally likely to take any value, the whole this one. Okay, so that is about this one. Then, what will be the expectation of x? That we have to use the standard formula and get it. But from the fact that this is symmetrical about mu, okay, then the expectation has to be mu, because around mu on either side you are taking the value, the actual value of x, and then weighing it by the probability and then summing it over. On both sides of mu for a given, that is mu minus a and mu plus a are given the same weightage, and it goes like that. So the expectation has to become mu. So mu is nothing but the mean, and the sigma, okay, decides how the distributed the values of the normal distributions are there. How much it can vary away from the mean. So it will turn out, as we will see, that sigma squared is equal to variance. We will write it, but we will show it. So the normal distribution x is given by two quantities, the parameter mu and sigma squared, which we have been treating as only parameters so far, actually signify the following things. One, the mean of the Gaussian distribution, and another the variance, and the sigma is the standard deviation. Is this it? Please here. Not now, it will take time. Well, I think I will start writing from this one. I will be later on projecting something. Well, now what we will do is, so is this normalizable? That we will quickly check. Why is this quantity 1 over root of 2 pi sigma squared, and all this complex quantity, why should it be like this? Why should it take a form? See, this bell-shaped curve is because of this one. Okay? That will always occur because of this. Why this factor like this comes? Okay? That is because of the fact that it has to be normal. We will consider this quantity. See, if you want to be fx of x, has to be normal. Equal to 1. This is what we expect. So what we will do is, we will look at only this quantity. We will look at a quantity q, which we will write it as minus infinity to plus infinity e power of okay. We will look at this quantity. First and foremost, what we can do is, if you put x minus mu is equal to u, then dx is equal to du. We can alternatively write it as, so q is also okay. Then this is q. Let's look at this quantity. Why later on what happens is, this is the what we are being leaving this one, we are computing this quantity. This integral, taking out this one, is what we are going to compute. That is what we are calling as q. Like this. Well, now what I will do is, now dx I have put in, actually I will put it as x squared dx. Oh, I have changed it to u and then du, okay. Then you will have u squared du, is all what we will get. Now, it's all dummy variables. I can change it to u, x, or t, v, whatever it is. So I will take two quantities. One is q is equal to, that is minus infinity plus infinity, e power of minus half x squared by sigma squared into dx. The same thing y squared by sigma squared into dy. They are all same, only the dummy variables are changing. And I will multiply. Then you can write q squared is equal to, that is minus infinity plus infinity. When I multiply these two exponents, then what will happen? I can add it here by the same sigma squared here. We can write it like this. This is what we need to compute. So this is a integration in the xy plane, in Cartesian plane. We will convert from Cartesian to polar. So by introducing r and theta, x equal to r cos theta, y is equal to r sin theta, and so on, we don't need to get into all those things. But you know that how the integration changes. You will have here dx dy as the infinitesimal for integration. In the case if you go to r and theta, what you will have is something like this. This will be the corresponding area you will get mapped onto, where you have to integrate. And what is this area? This is d theta, this is theta, this is d theta, and this is dr. To get the area, you have to, the area will be r dr d theta. That is the area, not just dr into d theta, because okay, r into d theta is this quantity, the sector one, dr is this one. This is what you have to do. So what you have to do is you have to change the limits appropriately, what r and theta can take, and change dx dy to r dr d theta. So now changing to this one, first theta is 0 to 2 pi and r is 0 to infinity e power of minus 1 by 2. This I will put it as r squared, x squared plus y squared is r squared by sigma square into r dr d theta. Right? This will change. The integration over theta is very simple because these are all r related. So if you take theta here, then it is just to 2 pi. That's all what you get. R dr. Okay. Now if you put r squared by 2 sigma square to be equal to, let us say, t, then what will happen? 2r right, that is equal to r dr is equal to sigma squared dt. So the whole thing, if you try to replace it as t, then 2 pi into, what will happen is 0 to r. There is a sigma square dt is there. R dr becomes sigma square dt. So dt I will keep here. Sigma square I will even bring it here. And e power of minus t. Okay. This is what you get, and that's it. So this is nothing but e power of minus t by minus 1, 0 to, sorry, this is infinite. Why am I doing this? Or actually we have to integrate to find, this is what we are trying to find. then infinity. So this we can 2 pi sigma squared into. Actually we will have again a minus 1, 0 minus 1. This minus 1 will come here, this will become 0, and if you put here minus 1, so basically it becomes equal to sigma squared. So this becomes 1, actually that's what it becomes sigma. So what are we finally getting? Q squared is equal to 2 pi sigma squared. Q is equal to root of 2 pi sigma squared. Okay. So what we are seeing is, so in this one, where did we start off with? Yeah, in the top one, if you take 1 over root of 2 pi sigma squared and then doing the remaining integration, that becomes root of 2 pi sigma squared, then it becomes normalizable. And that is why we have put 1 over root of 2 pi sigma squared. Okay? So, hope it becomes clear why we are doing that. Q. But we have split this into, we have taken this one and this we have called it as Q. Later on we have computed Q to be this one, and then f of x becomes normalizable. That is one. So first thing is it is normalizable, and its expectation also we have seen. Then we will look at the variance. So meanwhile, Ankit, you can try to keep everything ready. So variance is what? How to compute it? Minus infinity to plus infinity, 1 over root of 2 pi sigma squared into x minus mu the whole square into e power of minus half into this is the variance. What we have done? See, this is the density function. We have given a weightage of x minus mu the whole square and then integrate it out. That is by definition the variance. Mu is the expectation. X minus e of x the whole square. That's what we have to do. Well, then what we will do is that is equal to 1 over root of 2 pi. Here there is a sigma, and then we will now put x minus mu by sigma equal to u. Okay, a substitution. Then you can get that dx is equal to sigma du. So I have already taken this one out. Yeah. Okay, I will do one more thing. It's not this one. Okay, yeah, another better substitution would be x minus mu is equal to y. Then dx is equal to dy. Okay. Then what will happen is this will be y squared into e power of minus y squared by 2 sigma squared into dy. This is what we will get. So here what we will do is we will do it by parts. We will take one y, and this is nothing but d of we will take one y here If you do like this one, then what will happen? We have to put minus 1. You can put it like this. This y we are retaining, and this one is minus minus goes 2 goes sigma squared comes. There is a sigma squared that is coming. Okay. To avoid that one, we have to multiply it by sigma squared. Okay. We have to multiply it by sigma squared. That's it. Now, why this one? So it is nothing but the whole thing is pretty big. This one will be y into this function. We have to put the limits. This one will vanish. Okay? And then what will happen is minus of and this one. Again there is a minus will come. Okay. That will become plus. Yeah, here, like this it will come into dy. Okay. Actually, one more thing we can do, that we can do a change in, I think, x minus mu by sigma and all. If you put, even the sigma square can be eliminated. Finally, what you will have is, you will have something like minus infinity to plus infinity, e power of minus y squared by 2 into dy. A function of this kind. The only thing is this is extra remaining this. This will be, it turn out to be, it cannot be analytically done, it turn out to be root of 2 pi. Okay, and then on multiplying that, root of 2 pi and this one will go. And if you do that summation, actually we should have done that. This one is equal to y, then this is sigma dy. That sigma dy that we have got it here, okay, sigma dy, and that one, that sigma will go away, this sigma squared will remain, this 2 pi and root of 2 pi will go away. What will remain is nothing but sigma squared. This is what will be the variance of x. Okay. So variance of x is this. Finally, the CDF. Okay, so this is the cumulative distribution function. Sorry, again this is yes, I will change it to what? This is the cumulative distribution function. Again, what you can do is, by a similar change of variables, you can actually write it as 1 over root of 2 pi into minus infinity to s e power of minus a new variable u squared by 2 into d. Okay, and this is called as the CDF. This is the CDF of the Gaussian random variable. Yes. Gaussian random variable. So, can you have it properly? Yeah. So this function is not something that you can easily compute, okay, analytically. So all these can be numerically computed, and it has been done and it has been tabulated. So the CDF of the function has been computed and it has been tabulated, and this is a different one. Can you plot the other one? Can you project the other one? So you can use this to compute CDF. Or one more thing I can do is, for x greater than 0, what you can do is, I can split it to minus infinity to 0 plus 0 to x. The same integral can be split into 2. And you know what is this quantity will be? For an x greater than 0, if you want to compute the CDF for an x greater than 0, the integration from minus infinity to 0 will be the integration of 1/2 of the symmetric bell-shaped curve, and that has to be equal to 1/2. So this will be always be 1/2. So the other way of writing is 1/2 plus a quantity which is 1 over root of 2 pi integral 0 to x e power of minus u squared by 2 into d. Actually, even if x is not greater than 0, it is valid. The limit, if you take limit like this and then here, you can go like this and come here. The sign will appropriately take care of all these things. You can always split it in two different manners. This 0 need not be between minus infinity to x. Then also it is valid. So this is also one more quantity that is important. So these have also been tabulated, and that is called as the error function. Of course, you can find out why the name is being given for this one. To do with something, because all these things grew up because of the statistics and so on. So E or F also, error function. Okay? Evaluated as x, which is nothing but this quantity. 1 over root of 2 pi 0 to x into this one. If you use this one, then you will be able to compute the what? You'll be able to what? This is the CDF. So what is the one that we can do is, with this one is, this complementary cumulative distribution function I don't want. The error function complement, C is that. That is look x to infinity. So that is also can be used. Let us not get into that one. Why don't you put it? You put this one itself, CDF itself. You should have CDF. So what you can do is, you can compute, for example, this is one thing. Then one more thing that is very important before I have to introduce is that is standard normal Gaussian random, standard normal distribution, and that can be used as a way of computing the probability statistical quantity of any distribution. So n mu sigma squared means it's a mean mu sigma squared variance. Supposing you have a mean of 0 and variance of 1, then it is called as the standard normal distribution. It is only for the standard normal distribution the error function and the CDF have been plotted. These tables correspond only to the standard normal distribution. Okay. See, suppose if x is normal with mean mu and sigma squared, why don't you not this one? You choose CDF you have plotted. Huh? That's okay, but the full table which should be there. If you have this one, n is equal to mu plus sigma square, then suppose I define a random variable y, okay, which is defined to be the transformation x minus mu by sigma. look at the nature of y. X is normal with mean mu sigma squared variance. Y is defined to be x minus mu by sigma. It's a transformation. Then, if you find E of y, what is this? See, this mu, sigma are all numbers, just constant. So, by this is what you will get. Because if you take an expectation here, you have to take an expectation of this minus expectation of mu, which is mu, and a times expectation is expectation of ax is a into e of a, this one. So sigma is a constant, will just come here. And we want these two are the same thing, which means that this is equal to 0. So expectation of y is 0. And what is variance of y? If x has got variance of x, what is the variance of a times x? It is a squared into variance of x. Okay, it gets squared. So this can be written as x by sigma into mu minus mu by sigma. If you take a variance, you can just take individually. But what happens? This is both are constant. Its variance is 0. So it is only variance of x by sigma. It becomes 1 over sigma squared into variance of x, which is again sigma squared by sigma squared, that is equal to 1. Which means that y is standard normal. If x is like that one, then normal. So if you know, so you can any Gaussian random variable can be transferred to a standard normal distribution. Okay. So suppose you want probability that x, okay, x is less than or equal to x. This is what CDF you want to find for a general random variable. Then what I will do is I will do the transformation. X minus mu is less than or equal to x minus mu. This is right because I am just subtracting this one. I can also write x minus mu by sigma is less than or equal to x minus mu by sigma. See, this is a sigma is a positive quantity, is not going to change inequality, nothing. Okay, so you can write it like this. So what is this one? This has become the standard normal random variable. So that is equal to probability that y is less than or equal to x minus mu by sigma. So what it does is, x is any Gaussian random variable for a given mean and variance. If you want to find this kind of a CDF of x at small x, then you find x minus mu by sigma and look for the CDF of a standard normal random variable. The same probability, both properties will be the same. So to again I will sum up, given an arbitrary standard Gaussian distribution, the mean mu sigma squared, you want to find the CDF at the LAX, you find x minus mu by sigma and find the CDF of a standard normal random variable. Its probability will be the same as this. So how do we find it? That is what is given in this table. For example, if let's say if you want to find the so let me just put it. For example, if mu is equal to 1, x equal to 2, and then sigma is equal to 0.5, then what will happen? X minus mu by sigma 2 minus 1 by 0.25 is what I will get. Okay, this is not a very good this one. So it is 1 over 0.25. It will get 4, right? This is what will be 4. Okay. So you have to then look for the value of this CDF at 4. 4 is not a good number because it will become so. It is not even plotted here. I think. Yeah, that is a very large. If you want to find for this quantity, for example, for 1.75, if you want to find, if you find that quantity x minus mu by sigma to be 1.75, its CDF if you want to find. So this is an error function only of that. What you have to do is, this is from 0 to infinity. Where is this? error function is 0 to infinity is what is plotted here. If you want to find CDF, you find this one using this table, add half to it. So if you want to find for 1.75, then what you have to do? CDF first. Probability that y is less than or equal to 1.75 is what we have to find. Then you find the error function at this 1.75. That is 1.7. Go here. Find here. 0.98667 is the value, and yeah. This is 0 and minus t is equal to 0 to x. Okay. No. No, this gives the actual CDF. Actual, because it goes to 1, it nears approach to 1. Okay. So this is how we have to find. Find the value. This one, for example, 2.3 means you have to go here and then you have to find this one. Okay. So that way you will be able to do. To get a more how you can use both these the CDF means if you give you an area, if you evaluate at a positive x, it will give you this area. This is what the CDF will be. You use this symbol to denote the CDF of a Gaussian random like this. I think you can stop now. Yeah, you use this kind of a one. If you want to find